Hello and welcome back to CET3116. In this video, we will continue studying counters. We just analyze and review some report counters. Now we want to see some parameters and the reasons why report counters are not such a good solution, and that for that respect, we then turn into synchronous counters. Okay, remember when we study flip-flops, we study certain timing parameters. You want to see that these parameters are very important as the key to design counters. So one thing is the setup and hold times. If you remember, the setup time is the minimum time that this input value should be stable before the clock comes. Similarly, the hold time is after the clock comes. In general terms, we still need to keep the whole time ensured, in other words, that the input value of the variable is maintained right after the clock for that particular time. Okay, so after the transition of the clock. We also discussed the propagation delay, and the propagation delay is whenever you change the input in any device, when this output is updated, this difference of time is what is known as the propagation delay. In the case of the flip-flop, we have two. The transition of the flip-flop could be from 0 to 1 in the output, of course, or from 1 to 0. Whenever we talk about from 1 to 0, that's what we refer of the propagation high to low. And the propagation low to high is the one that references the time between 0 and 1, or low to high. Okay, we also have another parameter we never discussed before, and this is the maximum clock frequency. Although we could derive some parameters regarding the maximum frequency, and we did some examples with the D flip-flop. If you remember that we did a feedback with an inverter, and we sort of deduct the basic numbers, or the basic expression for the maximum frequency that will correspond to the minimum clock period, if you remember that. Well, that in general is a parameter that also is given in the specs of the flip-flops. And as another important parameter that's given as well, we have clock pulses high and low times. Not necessarily in the the very strict sense of the design, both clocks needs to be the same size. In other words, if you remember, I mentioned that we may have clocks, and the proportion or the ratio on which the clock remain high and remain low is what is called the duty cycle. So typically, a clock that is equally high in time and low is called a clock that is 50% duty time. All right, so, and in this case, the clock pulses should have different times for high and low, and that's what essentially says in here. So with this in mind, then to remember, for a setup, we're gonna clock the input, or the flip-flop, and actually we have this measurement of the setup time. This is our input. Okay, this is, in this case, for instance, could be the input. That should be a change. You see, the transition is not immediate, and then we're sort of taking that into consideration. At a certain point, usually in the middle of the rising in the input, measure from that point in the middle of the rising, of the highs, to the middle of the rising height of the clock. And that's what we call the setup time. And this is exactly the same thing for the whole time. So this is the clock. The clock is going up, and the input needs to be still kept in the input stable. Okay, so the whole period or the whole time and the setup and plus the whole time the input needs to be stable in the as a read in the input. Okay, good. And with respect to the propagation time, we can depict something like that. If this is the clock and the input somehow is performed at the point of the clock transition, that's when we're supposed to read the clock. And in general, we assume that. Suppose the input is stable at some point. At this point, we're assuming that we are reading this input, and then the effect is that we want to see the output change in the in this case from low to high. This is Q is low and goes to high. We assume that also the change takes place at the 50% of the level in the output. Similarly, when we have the delay going from high to low, so this is a propagation delay, high to low, and then the clock changes, the output is initially high and then goes to low. At the middle of this transition, high to low is what we are supposed to measure. All right, so in any case, we know that this time exists, that we do not have an immediate response from the input to the output. So in other words, we need to respect that time. We have mentioned and we have done some cases in which we analyze this time as a compromise or a time that has to be respected. In this example, I will show that depending on the clock cycle, we may have more problems if the clock cycle is smaller. See this case. In this case, we have a ripple counter, okay? And we have a clock in which the cycle is 1000 nanoseconds. See, if we have for each one of the flip-flop 50 nanoseconds of propagation time, that means that if you remember how the ripple counter works, the first flip-flop will change after 50 nanoseconds on the transition high to low of the clock. Okay, we're assuming that those are JK flip-flops and they're falling edge type of flip-flop. So we have 50 nanoseconds of propagation time. Remember, this output of the first flip-flop is going to be the clock that feeds the second flip-flop. That's the way the ripple counters are designed. And therefore, our clock will go late 50 nanoseconds, right, into the next flip-flop. Okay, because that clock, the output of the second flip-flop will be the clock of the third flip-flop. At the end, if you add each one of the propagation times, we will have 150 nanoseconds. Well, at this point, because the clock is, in this case, rather slow, we see, well, 150 nanoseconds compared with, 150 nanoseconds compared to 1000 nanoseconds. That doesn't actually complicate things. So you see, well, pretty much the timing are respect. This is the transition high to low is followed by this transition high to low is followed by these two transitions, and so on and so forth. But here, in this case, we reduce, for the same ripple counter, we reduce the clock period to 100 nanoseconds. and see what happens. What happens is that, okay, we now have the same propagation time. We have 50 nanoseconds, and we are basically moving to the first part of the next clock, right? And that's because of this. And well, we add another 50 nanoseconds, and that we're completely one clock cycle off in the output. And the third will add another 50 nanoseconds, and total 150 nanoseconds, similar to this situation. But if we compare with the clock, then we're off more than one cycle between the clock and the output. In other words, we're one cycle and a half. In other words, if you're looking and measuring the timing of the clock and the timing of the output, we're completely shift and off. So that's pretty much, as I mentioned before, the worst part of the ripple counters. That's why I mentioned they're rarely used. They're not attractive to use because of this problem. The other thing is that are really easy to do, and where we have some other applications for the ripple counter. Okay. Now, what is the solution? The solution for that is simple. So, in other words, if we manage to make possible that the timing is equal for each and every one of the flip-flop, in other words, they change at the same pace and at the same time, that's what exactly is a synchronous counter. So each flip-flop will be connected to the clock pulse. So it's sort of we feed the clock in parallel. And then as a consequence, we have that each and every one of the clocks are fitted at the same time or change at the same time. All right. Let's see one example, very easy, on how a 2-bit synchronous counter is set. We have these two JK flip-flops. The first flip-flop is timed as toggle as before. However, the second flip-flop is not. It's fed directly with the JK tie, but not necessarily to 1. Remember, Q is going to be, this guy is going to be toggling. So Q is going to be changing from 0 to 1, 0 to 1, 0 to 1. What happens if, in this case, when we are 0 here, Q, the first flip-flop is 0, what do we have here? We have a hold. So the clock will come and will keep the output the same. When this guy, the first flip-flop, is 1, then we're going to change that because it's going to be a toggle. So this is the case of the first flip-flop, which is normally the same thing as we've seen in all the counters, in ripple counter that we study. See, this is nothing different, exactly the same. This output of the flip-flop goes 0, 1, and then next toggles goes to 0, and then toggles again, and so on and so forth. Of course, when we have F1 high here, that means that we have to toggle. Okay? At this point, you have to read, this is the point of interest. This is the point of interest. This is when this guy is going to change. However, at this point, you're going to see that we're reading actually, when that happens, FF1 will be actually in 0. There's a transition, and that's a bit of delay, so we are not reading a 1. Okay, we assume that this 0 to 1 transition here is after this guy goes, the clock goes from 1 to 0. So therefore, at this point, we're reading is a 0. Okay, and we have a hold from a 0. We're supposed to have this cleared, right? Both FF1 and FF2. And then now we read a 1. Okay, we are reading a 1, the next transition, and then that corresponds to a toggle. Okay, in this case, we have a hold, the 1 stays, and then now we read again a toggle at this point. Therefore, we go to 0, and so on and so forth. So this very simple concept, but very powerful. And the main feature is that everything changes at the same pace, synchronously. That's why we call a synchronous counter. Okay, let's extend this idea to a 3 bits. Okay, I'm gonna see that the approach is slightly different. I mean, it's the same approach, but we need to solve something here. All right, I'm going to show you how exactly the 3-bit small synchronous counter work in terms of the truth table. Okay, this is very simple. Right, this is the count. We start with 0, 0, 0, 0, 0, 1, 0, 1, 0, and so on and so forth until we reach 1, 1, 0. Now, see what the approach of the first case of synchronous counters was to make possible that the flip-flop that guides the output is either in, for instance, if you see this 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, it's clear that this guy is toggling in every row. This is toggling in 2. And then the idea is because we're using a transition from the first output, 0, 1, then obviously in this case, we're going to consider, well, first we have a hole, then a toggle, then a hole, then a toggle. And so we're sort of using 2 cycles to generate one output in the following column or the following bit. However, in this case, we need to approach this differently. So see that I need to force to the most significant bit, in this case is C. It will change only at the 4th, right? On the transition from the 4th to the 5th row, okay, or transition. And then we need to force that when? Well, what I could do is see exactly what are the values of A and B for what this value needs to change or need to go on or do a toggle between this 4th state to this one. How do we do that? Well, very clever. This is the way we do it. So see, I want, according to this, change C whenever B and A both at the same time are 1. This is what I'm using, this AND gate here. T, the point of interest here, will be 1 only with these 2 inputs here are 1, A and B. In other cases, T will be 0, so that will be a hole. And then, using that as an approach, well, we see exactly the same thing as we did before with the first flip-flop, always tied to 1, always toggling. The least significant column always toggle 0, 1, 0, 1, 0, 1. So this is not that difficult to follow. In this case, well, that's what we have in the first example of synchronous, which we tie that. But for the third, I need to be sure that only we change when these 2 reach 1 to 1, and they stay there until the next time these 2 reach 1 and 1. Okay? So the flip-flop 2 will change pretty much following the same feature as before. And then, well, the third flip-flop will follow according to what the value here of T. And this is what we have, T. T will be 0 for the first count, if you remember the truth table. Also, in the second clock will be 0, that means a hole, and the third will be a hole. But whenever we find that A and B are both 1, then we need to toggle. Okay? And then that will correspond to a 1 here. So we have 1 and 1, this is going to be 1, and this is a toggle. Later that, they will change, and then we have a 0 or a hole, 0, 0, and then again a toggle, and then go back to 0. All right? So we can extend this idea and look into the truth tables. I'm going to show you later the example with 4 bits, and essentially that's an idea that can be extended. The only thing is that, remember, at some point we need to be careful with the number of gates that we're doing. One gate like this introduces some delay. Of course, it's going to be only one per stage, okay? And we want to have some examples of that. Good. Well, next we're going to be talking about down counters, and I will quit this for now. We want to see down counters in ripple counters. We want to see them come back with synchronous up down counters, and want to be looking into some interesting examples of counters that are that come in terms as a packages or integrated circuits. Okay, well, don't go.